Hey, welcome to Bio 100 again. Hope you had a good Thanksgiving. I apologize I haven't posted a lecture in a while. I was actually pretty sick for a few weeks. I think I'm on the mend now. So let's go ahead and wrap up the semester. And a good way to do that is to talk about human population growth. So, what have you heard about human population growth? I want you to think about that for a minute. Is it out of control? Is there not enough? What have you heard about it? Okay, so while you're thinking about that, let me introduce some ideas. So we could talk about ecology, which is really the study of interactions between organisms and their environment. And it's very much focused on populations. Populations are the heart of ecology. So populations are essentially all the individuals of a species in a given area. The total number of individuals in a population is what we call population size, and then population density is the number of individuals per unit area. So let's talk about changes in population size. So populations are going to change over time. Almost all populations will. It's dependent on environmental factors such as birth, immigration, or decreasing factors such as death or emigration. So if you look at England, where probably a large part of our ancestry in our class comes from, the UK, if you look at this, you can see that there are major epicenters of population here, right? So that you can say the population of the UK is one size, right? But the realities are is that that population is not evenly distributed throughout the UK. You've got areas like London here with massive amounts of population, and even capitals in places in Wales and other places where they have high population rates. And these are all things that that can play into population sizes. So as you can imagine, because that population sizes aren't equal over all the landscape, estimating population size is very important. It's an essential part of ecology. So populations can be measured in a variety of ways. We do like a basic consensus where literally walking door to door or measuring all the trees in a forest, but all individuals are counted. And then you can have something like a mark recapture, which is kind of estimating, where some individuals are trapped. You mark those individuals, you release them, and then you go back and catch them at a future date, and you kind of do a ratio of how many individuals are later captured, and that helps you figure out the overall population size. So here's an example of a mark recapture. So a researcher captures 100 beetles in a trap. Okay, he's going to mark each with a small dab of paint. After a week, you set the trap again, you come back, and you look at how many individuals in the group are marked and unmarked. And then the total population is estimated as a percentage. And so here's how the population works. Okay, so you've got capture 2 over capture 2 marked over capture 2 total over total marked from the first capture, right? That gives you the total population, an estimate of the total population. Okay, so here you can look at it here as well. Animals captured on the second day, size of the sample on the second day here, animals marked and released. Okay, and then this is going to give you your population size, and then from there it's just simple algebra to finish it. So let's kind of jump in and do an activity. And I apologize. I actually should have changed this. My TA wrote this up several years ago, and I keep meaning to change it. I did not write this question. But when you look at it, suppose you want to know how many dragonflies are in a pond at your local park. On the first day, you hunt and net 24 dragonflies in 8 hours. You mark each with a dot of black permanent marker. 3 days later, you return with Dr. Bybee and catch 60 dragonflies in an hour. He catches 58 of them. Again, this was not me who wrote this. Of these, 15 are marked and 45 are unmarked. Use the data and the equation below to figure out the population size. So what I want you to do is just hit the pause button and figure out an estimate of how large this dragonfly population is. Okay, hopefully you're back with us. So if you break down the question, you've got 24 on the first day, right? You've got 60 on the second day that were caught, and then you have 15 that were recaptured. So now we just have to solve for n. And if you do so, it comes out to be 96 individuals in the population. So there's also some other things to consider here when you're talking about doing these mark recapture studies or other things, right? That you want to be careful where you're doing them and when you're doing them. So here's an example of an astragalus from Utah. They're found in rare soil types. They're very specific to southern Utah. During drought periods, reproductive adults won't even emerge from to flower, just because it's too dry to put in that amount of energy. So a study where individuals were tagged and monitored, they had over 60 adults were observed in 2006, and then they went out the exact same time of year and looked at and trying to find adults, and there were no emergent adults that were recorded in 2007. So, but 30 of the 60 adults recorded in 2006 emerged in 2008, right? So you can just imagine, if you're trying to do a mark recapture type study here with these plants, that you have to be aware of their biology to get an accurate reading of the actual population size. Dipsosaurus is another one. So these adults are mostly active in the late summer to fall. So if you're going to mark them in the spring, it's really unlikely that you're going to mark adults. But only juveniles are going to be marked if you work in the summer or fall. So you kind of have to also consider the timing that you're going to do these mark recapture studies as well, right? That sometimes you can't do them within the same season, or if you are going to do them within the same season, you need to do it at the beginning, middle, and end, something like that, to get an accurate measurement. Okay, so we talked about population structure as well. So populations are dispersed over a large landscape. Remember what we looked at on the map of the UK, right? That there are so many people in the UK, but they're really not distributed evenly over all the land. You can have uniform distributions, or nearly uniform, and this green square is kind of something that would look like, but it's essentially that spacing between individuals tends to be pretty equal. Random means there's no compelling feature pushing individual targets right here or apart. And then clumped, these are high density, resource rich areas, low density elsewhere. So if you think about human populations tend to be clumped around water. Resources is one of them, but also larger cities, things like that. And then you can kind of think of more random sizes here. Human populations, trying to think where you think human populations might be more randomly distributed, and then where might they be nearly uniform. There's something to think about as well. Okay, so looking at human populations, here's an overview of it. So archaeologists can estimate the size of the human population to about 10,000 years ago, and the human population is an example of what we would call exponential growth. And exponential growth is in proportion to population size. So right now we are approaching exponential growth with COVID-19 in the human population, because it's starting to actually skyrocket, not only in the US but around the world. Although luckily there are enough humans making efforts that the COVID-19 spread is not exactly exponential yet, luckily. But when we think about this in terms of a population, as population grows, growth also increases. So that's what you're talking about, right? As something grows, growth increases. Now that might not make exact sense, but hang in there with me. Okay, so historically the human population was about 1.1% per year. Okay, so that was about 2,000 years ago. But by 1750, this is when there was large amounts of industrialization going around the world, improved agriculture, things like that, it was about 2% per year. So the current growth rate is 1.2% per year, and the current population, so we're up over 7 billion now, but about 1.2% growth rate means that our population as humans increases by 84 million people per year. Okay, so consider a growth rate and time it takes to double. Okay, so here's your growth rate percentage on the bottom, time and population until the population doubles on the y-axis. And when you're looking at this, so if it's a 0.5 population growth, it takes about 139 years. All the way up to 2.5 only takes 28 years. So where is the human growth rate right now? Well, traditionally it's been very low down here. So it would have taken, close to maybe 150 or 200 years for the population to double at that rate, maybe even more. And then we have been as high as 2%, which means the population doubles every 35 years. But right now we're about 1.2%. So somewhere between 70 and 47 years for the human population to double. So let's learn a little bit about human population. Let's go here and we'll watch this. Actually, we're just going to watch this link. I've already loaded it here.
Only 1/3 of a billion people, but we were
Sorry for the technical difficulties. It's worth it.
1,000 years ago, there were only 1/3 of a billion people, but we were multiplying. Now there's 7 billion of us. How did we grow so much so fast? Say this glass is North America. The fuller the glass gets, the more people there are. Water drips in as people are born. Water drips out as people die. Okay, here's the entire world. Now let's go back 1,000 years. The Americas are nearly empty. Europe and Africa have less than 100 million people between them. And just like today, most people live in China, India, and the rest of Asia. For centuries, things stay pretty much the same. Births are canceled out by deaths. Women are having lots of babies, but most babies die before they grow up and have families of their own. We don't reach 1 billion until 1804. But things are changing. Better medicine and better agriculture are starting to slow the leak from the bottom of the glass. People still die, of course, but more babies grow up and have babies of their own. Lots of babies. We've grown from 1 billion to 7 billion, and it only took 200 years. Will we keep going like this? Probably not. The UN says we'll level out at 10 billion by the end of the century. So as we continue to grow from 7 billion, the question is, can the world hold that many people? Experts can't agree. It all depends on how well we manage our food, water, and energy.
So kind of provocative and something to think about in terms of what this means for human populations. So let's normally we would do an activity at this point in time, and what we would do is we would have some of you pretend to be foxes and some of you pretend to be rabbits, and you would play a game. And what we'd find out pretty quickly is that as the number of rabbits increases, so do the foxes. But as rabbit numbers increase to the point that their environment can no longer sustain them, then the rabbit population crashes, as does the foxes. So what we see is that there's actually this following between foxes and rabbit populations. And it looks something like this. If we had played this game and you had graphed it as a class, this is what we would see. Somewhere where the rabbit populations are really high, you see the fox population not exactly in line with the height of the population, right? Because foxes are preying on the rabbits, so they follow them a little bit, but they're crashing just after the population crashes, and then they're peaking just after the population peaks. And this is what we call these boom or bust cycles, and we'll come back to this in a little bit. So generally in human populations, though, a decrease in death rate is followed by a decrease in birth rate. So these are called demographic transitions, and you can see some transitioning here. But before the Industrial Revolution, both birth and death rates were high. With industrialization, though, improved sanitation, medicine, etc., death rates decreased, and so do birth rates. But there's a lag time between this decrease in death rates and this decrease in birth rates. And this lag time has a major impact on population size. Many developing countries are still in a demographic transition from this. So here's what we're looking at. So you have very high birth rate and death rate, and what you can see is the population down here is just not really going to grow. But as those death rates decrease and the birth rate increases, the population begins to grow, but not extremely quickly, right? Like there's still some sort of, they're on an upward trajectory, they're moving up, but it's not really fast. And so when you're looking here, but as this population grows, something happens. So the birth rate will decrease tremendously, and the death rate will kind of settle into a pattern. And as it does this, because the population here got to be so large and in here got to be so large, that there's actually, it takes longer for the population to decline overall because of the amount of population size here. Hopefully that makes sense. Hang in there for a bit. We'll come back to it. So populations have the potential to grow exponentially, but they're going to be limited by environmental factors. Remember the fox and the rabbit situation. So they're limited by food, water, shelter, and space. So you can have this exponential growth, but eventually they're going to hit this line, which we call carrying capacity here, and they're going to hover around this line. So this is the maximum number of individuals that can be supported in a given environment. So studies on non-human species, we see this all the time, that no population can grow to unlimited numbers. So we talked about the rabbit and the foxes being dependent on each other. There's other examples like elk in Yellowstone National Park in the 1970s. They had an extremely high mortality rate after large populations degraded the environment and there was no more food in the environment. Now, this happens quite regularly with deer populations back east, particularly where there are few hunters. The populations is a state that sticks out in particular is a state like Connecticut. There are very few deer hunters in a place like Connecticut, and yet there are no wolves. The predator populations are very low to maintain those deer populations. So what you see is these deer populations peaking, becoming outstripping their environment and dying. Norway lemming populations have also been known to grow to very large sizes, outstripping their resources. They become as the resources become very scarce, the populations actually undertake mass migrations where they'll just all pick up and move somewhere together. But I should also say lemmings do not jump in cliffs, in case that's anything that you've ever heard or wondered about. They don't do it. That was actually part of a Disney movie in the 1950s where the producers didn't know what to do, so they made the lemmings jump off the cliff into the ocean, and as a result, there's been this useless fact floating around in our populations that lemmings run into the sea when resources get short, and that's not true. Here's some other things. So there are density dependent factors. So these are factors that increase with population size. So as a population gets larger, there's going to be limited food supply, increased risk of disease, increase in waste levels. It can cause decreases in the birth rate, increase in the death rate, or both. The density independent factors, these are influenced by population. These are not influenced by population numbers mostly, right? So you can have drought, temperature extremes, and natural disasters. Now they say mostly because there is some evidence that human influence may affect things like temperature change in our world. Okay, so what resources might limit human growth? I want you to just think about that for a minute. And if you can't think about any real resources that might limit human growth, here's some links that you can follow on your own. Some other limits to population growth. So there's really uncertainty about the future of the human population growth rate. So recent growth rates have been as high as 2% just in the 1960s. So some of your parents were probably born around that time. And then growth rates are now about 1.2%, as we've talked about, but it's really unclear where we're headed in the future. So the UN has released 3 projections. So if we have this low growth rate, where the growth rate actually drops under 1.2%, we may settle in at just over 7 billion, although that seems pretty unreasonable at this point in time. It could be right, but we'll have to see. But there's a medium growth rate here, which settles in somewhere between 8 and 9 billion, and then the high growth rate settles in around 10 billion. So this are signs that the Earth is not near carrying capacity, right? We've talked about carrying capacity in terms of other animals. What would carrying capacity look like for humans? What might be some signs of it? Here are some signs that it's not near carrying capacity. One reason would be the declining growth rate. The growth rate of human population is declining. Not in every country around the world, but overall it is declining. And this is because humans have this unique ability to choose whether they have children or not, for the most part. Especially compared to other species of animals, humans are exceptionally unique in their ability to choose. Earth resources can be measured by net primary productivity. So this is the total amount of plant growth on the planet. So if the estimates of net primary productivity are correct, it indicates that the human population can be about 20 billion. Okay, but that means that humans need to eat only, and that all humans have to consume plant growth, and that this plant growth can be used for nothing else either, right? So we can't grow plants to enjoy them. We must eat those plants. We can't. It just essentially what it's saying is that all productivity of plants in this earth are meant to feed humans, and we estimate that the earth could hold 20 billion. But I'll just ask you this question right now: how many of you want to consume only plants? So we're talking we're talking no meat, of course, that's off the table immediately, but there wouldn't be things like dairy, eggs, a lot of these other animal products that you eat would be off the table. Here are some signs that the population is nearing carrying capacity. So the populations require more than simple plant food, right? So this NPP estimate that we've talked about might just be too high. It's difficult to estimate population impact on water supplies. Humans need a certain amount of food, a certain amount of water, but also they produce waste, right? And that waste often goes into water. Many essential supplies are non-renewable resources. I want you to think about this. What are the essential supplies to you? What do you think those are? We have material consumption is affected by lifestyle and affluence. For example, the U.S. accounts for only 5% of the world's population, but consumes about 24% of all resources. So that's not a sustainable way to live. And if the rest of the world decided to live like the United States, which the rest of the world tries to do in its own way, it doesn't make for a very sustainable world. Okay, so the future of the human population. Are we going to enter into this boom and bust cycle, or is it going to stabilize around a carrying capacity?
Easter Island is one of the clearest and simplest examples of a society that destroyed itself. Easter is the most remote habitable scrap of land in the world, an island about 4,000 kilometers west of the coast of Chile, settled by Polynesians about AD 800, and famous for the gigantic stone statues weighing up to 80 tons that the islanders erected and then eventually tore down. So there's been a long-standing mystery how the islanders erected these gigantic statues without machines on an island without any trees or sources of rope, and why they tore them down. The answer has come out from studies by archaeologists in the last several decades, and it turns out that when Polynesians first settled Easter Island, it wasn't a bare grassland as it is today, but it was covered with a forest, including the world's biggest palm tree. And the islanders began to cut down trees for the usual reasons, clear gardens, have wood for construction and dragging statues and canoes, build their houses for fuel, and they continued to chop down trees until around 1680 they chopped down the last tree on the island, at which point they no longer had wood or rope to erect the statues, but also without trees. The soil was not protected against erosion, and they couldn't go out to sea to harpoon tuna. So Easter Island society collapsed. Easter Island, isolated in the middle of the Pacific Ocean, when the islanders got in trouble and had wrecked their island. There was no place that they could turn for help. They had no place to which to flee and no friends whom they could summon for help. But similarly, if we wreck the planet Earth, isolated in the middle of space, there isn't any other planet or galaxy from which we can summon help, and there's no galaxy to which we can flee. So the collapse of Easter Island is a metaphor for what may be the collapse of global Earth society ahead of us.
So that's something to consider. Now, I don't know if it's that dramatic, but I want you to think about that. Are there parallels here? Is Easter Island really a metaphor for some of the things that we see going on in our world today? Something to think about deeply. Now, certainly we have technology and lots of people sounding alarms, so perhaps we won't fall into that, but it is something to think about. All right. Demographic momentum. So this is what we talked about earlier. This is the time lag between when humans reduce the birth rates and when population growth begins to slow. So even if parents reduce family size, their children grow and have children. So even when parents have 2 children, which is just replacement, the population will continue to grow for 60 to 70 years until it stabilizes. All right, so that's when we come back here. This is what we're talking about. So the birth rate decreases, the death rate stabilizes, but because of the size of this population, it's going to keep on growing over time just because these the children of these parents are going to continue to have children. Okay, a population pyramid with a large base here, okay, indicates the majority of the population is young and that the population is still growing. So here you have this large young population that's growing. Here you still have a very large young population. Here what you see is the population has actually kind of settled into a rhythm in this one. So we call this stationary. And then here we actually have contractive, where there was one where the older population is larger. This is what we would call, in the US, we have a boomer population, right? The boomers are sitting in here. And then there's smaller populations down underneath. So these are generally very slow birth rates, low death rates, longer life expectancy. So in the US, we're somewhere between these two right now. But there are areas of the world like Nigeria, parts of Africa, Asia, where they actually have populations that are more like this, okay, and then some emerging populations like this at other parts of the world. So something to think about. Where do these demographics that you're seeing here actually align with what we see in the world? Oh, and I should mention, areas of Asia and Europe are well into population sizes, population demographics like this, whereas the U.S. is kind of somewhere in between these two. They're definitely here. Okay, but for humans, as we mentioned before, there are other factors that can also affect population growth rate, and these include income, women's literacy, etc. There are social policies that can have impacts on human population growth as well. So here's an example: women's literacy here, and then it shows the population growth according to areas of the world where you have where women's literacy is very high, and where income is very high. Are areas of the world where you see some of the lower population growth. Okay, and so the question of how many people on Earth can support is really not just one of science. It's also one of values, and it's one of ethics. So here's the per capita income. Germany has one of the highest per capita incomes behind the United States, right? So we're looking at these. But then when we look at population growth rate, we see that the population growth rates are highly correlated with per capita income and also female literacy. So something to think about, how those are all tied together, and one of the things that's always been interesting to me is that as members of the church, we are told that we should multiply and fill the earth. And the question is, how do we do these things um, in a way that is supportive to our Earth? And that's a question that we really have to think about. So, my wife and I, we have a very large family, even for Mormon standards, with 7 children. Um, and so we've made the decision to do as much as we can to lower our footprint. So until recently, we owned a natural gas vehicle, which was essentially non-polluting. Even when you consider the fracking that has to happen for that natural gas to be excluded, to be pulled from the ground, it was less polluting than oil production. We also have a massive garden that we grow, and there are portions of the year where literally 90+% of what is on our table, and we're talking meat, vegetables, etc., even what we drink sometimes in terms of juice, has come from our garden, and that happens for a good chunk of the year. Generally, somewhere from June to October, we start to eat largely out of our garden and not anywhere else. And we've looked at how ways to expand that in terms of food storage, food preservation, but also greenhouse growth, that type of thing. So my wife and I also were pretty careful about the lights we put in our homes, our energy consumption. One of the things that always makes me laugh is whenever we do the carbon footprint, there are single students at BYU who have a carbon footprint equivalent to my entire family. Now that might not be the case anymore. Some of my kids have gotten older and using cell phones and other devices, but just the same, the amount of consumption that one individual can have can actually be quite high. And there are lots of easy ways for us to think about ways to decrease our energy consumption, and to become more self-sufficient in terms of food production as well. So anyway, I don't mean to be preachy here. I just want all of you students to kind of think about ways that you can just make very simple changes to decrease water, energy, food consumption. It's actually pretty easy to do, and one student over a lifetime can make a huge difference, and especially if that student can go and form a family unit that also has those same values, it can make quite a big difference. So that's where I'll leave it. Hopefully this was interesting to you. I also really enjoyed I really enjoy this lecture and thinking about human demographics.